Good morning students, myself Dr. K.M. Dadure, Assistant Professor Bajaj College of Science, Wardha. In today's class, we are continuing with transitions elements, and in that transitions elements, we are going to discuss a very important characteristics, general properties of the transitions elements. In the previous class, we already know that what is the transitions element, what are the D block elements, and what are the differences in between the D block and transitions concepts. And we also discuss the exceptional electronic configuration of the chromium and copper. Okay, so with that we start the general properties of the transitions elements. So in that general property, the first general property of the transitions element is atomic and ionic radii. So first of all, we will discuss the definition of the atomic and ionic radii. So what is the atomic radii? Students, the atomic radii is the simple distance between the nucleus and outermost electron of an atom, which is called as atomic radii. Okay, so in another word, if you want to discuss that same definition, so we can say that it is the distance from the nucleus of an atom to its boundary of the electron cloud. Okay, so this is also the one of the other definition and another definition through which we can understand what is the atomic radius. Now what is the ionic radius? So ionic radius is the distance between the nucleus of an ion up to which the nucleus has influence on its electron cloud. That is the definition of ionic radius. If you want to discuss the same definition in some another words, so we can say that the ionic radius is simply defined as the half of the distance between the two different atoms that are just barely touching each other. That is called as ionic radius. So let's see how this atomic and ionic radius is actually vary in the periodic table as far as the transitions element is concerned. So students, atomic and ionic radii of this 3D series element is found to be the decreasing when we are moving from left to the right in the period. And we all know that from left to the right in the period, the atomic number goes on increasing along with nuclear charges. And due to that increasing in the nuclear charges, they tends to attract the electron towards the nucleus. But don't forget, this as the nuclear charges goes on increasing, some other factor is also dominating over that nuclear charge, and that other factor is what? The screening effect. Okay, so here as the nuclear charges goes on increasing, but we also observe that some basically the atomic radii is actually not increasing in so much extent. Okay, so we can see that the decrease in the atomic radii is observed, which is to be less than expected. And the reason is what? Because of the simultaneously increase in the nuclear charge and screening effect. And as a result of these, the two opposing effect, the atomic radii do not change much from the chromium to copper. Okay, this is actually the reason. We can see the atomic radii is not actually the change in so much differences from the chromium to copper. And you can see here, this is the line which simply showing the linearity, and that linearity means that the changes is not occurring so much differences. Okay, in the same way, in the second and third transition series, we can see the trend is follow in the same order, around same order, but in a very close proximity. Okay, this is actually some different study. This is the different part of the study we will see in the second and third transition series in the detail. So but just focus how this line are actually the overlapping to each other as far as the second and third transition series is concerned, and that overlapping is giving you the information regarding the nuclear charges are increasing, but number of the properties of these transitions elements are varying, but not very in much differences. Okay, and that's why some other factor is actually increases, some other factor comes out through this way. So this is all about how this metallic radii is due to this how this metallic radii and atomic radii is actually there increasing or decreasing in this transition series. Now the most important and very interesting. Again, ionization energy. And students, we all know that what is the ionization energy, and as far as the term is concerned, we already repeatedly study this term in our previous classes, but here we will again discuss it, but we will focus on this term in the transition series. Okay, so let's define what is the ionization energy. So here students, ionization energy is defined as the amount of the energy which is required to remove the most loosely bounded electron. Okay, which is required to remove the most loosely bounded electron from the outermost shell from an isolated gaseous atoms of an element, in its lowest energy state. In its lowest energy state, it means that in its ground state. Okay, and to produce a cation, and is known as ionization potential or ionization energy of that elements. Okay, so students, here we will discuss the number of things related to the ionization energy, but let's focus on this diagram, and student, we can see that how this ionization trends is actually as per the definition point of view. We can see that this is the first transition series, this is second transition series, and this is the third transition series, and but we will focus on this first transition series, and in that we can see that the linearity is actually this linear line is indicating that the ionization energy is not varying in a much differences. Okay, in the same way, some two different line we can see here also the trend is going on, but not in a much differences. Okay, some little bit fluctuation is there, but the difference are very less. Okay, so this is actually the reason in the transition series, and this is actually the interest in the transition series. When we move along the first transition series from scandium to the zinc, the nuclear charge and number of the electron in the inner d sublevel is continuously increasing. Okay, and this increasing in the number of the electron in energy level is develop a screening effect and shielding effect. Okay, and due to this screening and that shielding effect, the forest electron from the nuclear force of attraction of the nucleus. Okay, due to this screening effect and shielding effect, the forest electron from nuclear force of attraction of the nucleus. Are you getting this, students? This increase in the number of electron in the inner energy level is actually develop the screening effect and shield the forest electron from the nuclear force of the attraction of the nucleus. Okay, this already we had discussed, and thus the effect of the increasing nuclear charge and the screening effect due to the expansion of the inner d sublevel oppose each other, and therefore the ionization potential of transition element increases very slowly along the transition series. Okay, this is very interesting part. Now let's see what is the oxidation state of the transition elements. So this is one another important part of the transition elements, and in that we can see some interesting fact. So student, as far as the oxidation state is concerned, so the transition elements are actually known for their multiple oxidation state. But before we going to discuss in detail, we will start with some basic point. Okay, and in that basic point we are going to discuss the S-block chemistry. So student, the S-block element have the property of showing the definite oxidation state because of the formation of the positive ion is related to the acquirance of the electronic configuration of nearest unit gas, and that is actually the reason in the S-block we can see some specific oxidation state. But the transition element is different from the S-block element, and in this respect, and we have found that there are the number of multiple oxidation state we can see in the transitions element, and that is the reason they show the variable oxidation state. Okay, in that variable oxidation state we can see here, this is the table, and this table belongs to this first transition series, which is start from scandium to zinc, and in that we can see that each and every element is showing the number of oxidation state. Okay, students, another important thing which is associated with the oxidation state as far as the transitions element is concerned, the transitions element, in addition to the acquirance of this stable configuration of the inert gas, they acquire other stable state such as half filled and completely filled. As far as the chromium and copper electronic configuration is concerned, in the previous class we already discussed how this chromium and copper is showing the exceptional electronic configurations, and due to that exceptional electronic configuration, that means half filled and completely filled, okay, a half filled and completely filled of this D sublevel, it means that they can acquire the extra stability, and they acquire the extra stability by achieving either by this D0 or either by this D5 or D10. Okay, so this is actually the electronic configuration which showing that where we can see some stability. Okay, so all the transitions element, but with exceptions of this chromium, copper, okay, this is the silver, oleums and mercury, exhibit the minimum oxidation state, and that is what? +2. And this exceptional element, it shows the minimum oxidation state of +1 due to the half filled configuration or completely filled configuration in its oxidation state. Get it? Along the transition series, the increase in the number of oxidation state is observed up to middle. Increasing in the oxidation state is observed up to middle as we move from left to the right, and then it goes on decreasing. So the various oxidation state is shown by 3D elements we can see in this table. Okay, so this is actually the very important nature which is shown by the transitions elements. Let's see how the transitions elements acquire the stability. As we discussed, the transitions element is actually they are taking the interest in half filled and completely filled configuration for getting and for achieving the stability. Okay, so here we will see the stability related to the scandium to scandium. So here we can see that those oxidation state in which ion gets empty, that means D0, and half filled, that means D5, or completely filled, that means D10, they are actually found to be comparatively the more stable. We all know that, and that is the reason from scandium is actually when in its a D state, and when D is actually having the 0 electronic configuration, is actually more stable than scandium, which is having the D1 electronic configuration. In the titanium, when this titanium is having the D0 electronic configuration, which is more stable as compared to when the titanium is having the D1 electronic configurations. That is, the titanium 4 plus is more stable as compared to the titanium 3 plus. Okay. In the same way, we can see that in the ferrous, this is the ferric ion, when it having the D5 electronic configuration, which is the more stable because it is the half filled stable electronic configuration, than ferrous, that is Fe2 plus, which is having the D6 electronic configurations. So with that, student, we are stop here as far as the general properties of this transitions element is concerned. In the next class, we will again we discuss some other general properties of the transitions element. So till then, thank you very much, and study at home with some reference books and some video lectures which is given to you. So thank you very much, students.